At this point, we're going to take a look at the ideal gas law. Now, I have to imagine that you remember seeing this in chemistry. And it's the relationship between the pressure, the volume, the number of moles, and the temperature of an ideal gas. And we're imagining an ideal gas that is confined into some kind of container. I'm not going to spend a lot of time going over solving for any one of these variables in this equation. It's very simple, and you've probably already done it in the past. One thing I will say is that in physics, we're going to express our pressure in pascals, our volume in meters cubed, N is in moles, and the temperature in Kelvin. If you do that, the value of R is 8.31 joules per mole Kelvin. What I am going to do is do an example showing how you can use this equation to compare two different states. So the example that I'm going to do is the idea of a bottle, draw a decent looking bottle here, with a cork in it. Now initially, the pressure inside the bottle is 1 atmosphere, which is 1 times 10 to the 5 Pascal. The temperature initially is 30 degrees Celsius, which is the same as 303 degrees Kelvin. We're going to try to eject the cork out of this bottle by placing it over a fire. When this is done, the temperature rises all the way up to 99 degrees Celsius, which is 372 Kelvin. At this point, the cork's going to pop out. The question is, what's the pressure inside the bottle when this happens? What we're going to do is we're going to take the ideal gas law, and recognizing that the volume is going to stay constant, the number of moles are going to stay constant, and R is always a constant, we're going to do the algebra that will get all of those things on one side of the equation and the pressure and temperature, which are our actual variables, on the other side. So the first thing I'm going to do is I'm going to divide both sides by T, and then I'm going to divide both sides by V. And I wind up with pressure over temperature equals number of moles times R over the volume. This entire thing is a constant, which means any combination of pressure and temperature will be equal to any other combination of pressure and temperature. And the way I'm going to write that is like this: P1 over T1 equals P2 over T2. Now in our case, what we're solving for is P2, so this is going to be a simple matter of multiplying both sides by T2 to get the following expression: P2 equals T2 over T1 times P1. Now the reason I write it this way is I just want you to see that there's a ratio of temperatures multiplied by original pressure is going to give us the new pressure. And that has to also work out unit-wise, because a temperature over a temperature is going to cancel out the units, and we're left with the units of pressure. So let's put the numbers in. Temperature 2 is 372 Kelvin. Temperature 1 is 303 Kelvin. Our initial pressure was atmospheric pressure of 1 times 10 to the 5 pascals. And when we multiply this out, we will get a value of approximately 1.24 times 10 to the 5 pascals. Now the important thing here is the process. First, take the ideal gas law, solve it so the variables are on one side and the constants on the other. Then set the side with the variables as a kind of before and after situation. Do some algebra, plug in the numbers, and you're done. You can do this for any situation, and you will have plenty of those situations to practice on your worksheet.